Here we have some geometric polynomials, and we are trying to write an expression for each and then determine if the polynomial is a perfect square. Let's of course start with number 1 and let's make it a little bigger. The polynomial expression is an expression of the area of the whole figure, and we want to do that by finding the area of each rectangle and each square and then add up all of the areas. Let's start with the area of one of the big squares. We do not know the lengths of the sides, but we do know the lengths are the same, so we are going to call this x by x, or the area is x squared. And we have 4 of them. When you add the areas of these 4 pieces, it adds to be 4x squared. Now let's do the area of each skinny rectangle. To do that, we need to understand that this length is still x. We do not know this length, and we are going to call it 1. So the area of the rectangle is 1 times x, which is x. Again, the area of each skinny rectangle is x, and there are 12 of them. And when you add 12 x's, we write that as 12x. So far, the area of the whole figure is 4x squared plus 12x. We still have, though, these little squares. And again, we are doing the area of each one. We just identified one side of it as 1 when we did the skinny rectangles, and both sides of the square is 1. When we do the area, 1 times 1 is 1. So the area of each little square is 1, and there are 5 of them. And when you add 5 ones, well, that's just 5. So this polynomial expression, 4x squared plus 12x plus 5, represents the area of this whole rectangle. The next question is the polynomial a perfect square? We know the answer to that is no, because this is not a square, it is a rectangle. Now that we have a little understanding, problems 2, 3, and 4 should go more quickly. Let's do number 2 by making it larger. We only have one x squared tile this time, and it might be tempting to write it as 1x squared here, but don't write the lead coefficient 1. Let's just put x squared. Remember, each skinny rectangle we label x, and there are 6 of them, so we write 6x or plus 6x. Each little square we label as 1, and there are 9 of them, so we express that as 9 or plus 9. Once again, our polynomial expression is x squared plus 6x plus 9, which represents the area of this figure, and this figure is a square, so we say it is a perfect square. I do want to point out that in a perfect square, the number of skinny rectangles this way will be the same number of skinny rectangles this way. Or in other words, half of them will be here and half of them will be here. Let's do number 3 by making it larger. We only have one large square, and let's write that as x squared, not 1x squared. We have 7 skinny rectangles. Each one of them is x, so let's write plus 7x for them. We have a bunch of little squares. In fact, we have 12 of them, and each one of them is a 1, so we write a plus 12, which represents the little squares. Again, the polynomial expression that represents this figure is x squared plus 7x plus 12. And since this figure is a rectangle and not a square, we put no for the bottom question. Now let's do number 4. Again, we have one large square. The area is x squared, and we write x squared, not 1x squared. We have a bunch of skinny rectangles, and each one of them is represented as x. We have 8 of them, so we write plus 8x. Finally, let's do all the little squares. The area of each one is 1. There are 16 of them, so we express that as plus 16. Again, we represent the area of number 4 as x squared plus 8x plus 16. And since this figure is a square, we put yes at the bottom. Again, I want to point out in a square, the number of skinny rectangles this way will be the same as the number of skinny rectangles this way. Half of them will be here and half of them will be here. Now, see if you can do problems 5 through 10.